Hello students, welcome to Educate. We are going to continue with chapter number 11 of 11th Physics, whose title is Thermodynamics. We have studied the basics of thermodynamics in previous lecture also, but once again we are going to restart with basic definitions and other related facts. You will enjoy the lecture. Let's see here. The definition of thermodynamics. Thermodynamics is the branch of science that studies heat, temperature, and energy transformations. It explains how energy is converted between different forms, particularly between heat and mechanical work. Thermodynamics focuses on microscopic properties such as pressure, volume, and temperature without considering molecular details. It is essential in physics, engineering, and chemistry for understanding energy transfer and efficiency. So here, what you have noticed in thermodynamics, mainly we see conversion, particularly between heat and mechanical work, right? So this is one important part of physics, or one important branch of physics, and it is used in chemistry also, in engineering also it will have certain uses. So we are going to see now basic definitions like thermodynamic system. What is thermodynamic system? A thermodynamic system is an assembly of large number of particles that have defined values of pressure, volume, and temperature, right? So pressure, volume, and temperature must be defined. It is separated from its surrounding by boundary, which can be real or imaginary. So you have seen what is thermodynamic system, right? Now we are going to see what is surrounding. The surroundings include everything outside the system. So two things we will consider here. If it is system, then outside is surrounding, right? The surroundings include everything outside the system that can interact with it by exchanging energy or matter. So here energy can be transferred in or out. Matter can be transferred in or out. The system and her surroundings together form the universe in thermodynamic terms. Correct? So whenever we talk about universe, it means we mean system plus surrounding, right? So you have understood this term. Now let's see next thing, that is thermodynamic variables. So generally PVT are called thermodynamic variables, but there are certain other terms that are included in it. So let's see. The thermodynamic variables are the measurable properties that describe the state of thermodynamic system. The most fundamental variables are pressure, force per unit area, that you know, then volume, space occupied by the system, then temperature, measure of the system's thermal energy, and the other variables such as internal energy, enthalpy, entropy, and Gibbs free energy also play crucial roles in thermodynamics. In chemistry particularly, we study these things. In physics, our study will be limited up to P, V, T, and U. Now let's see equation of state. Equation of a state. An equation of state is a mathematical expression that relates thermodynamic variables describing the state of a system. For an ideal gas, the equation of state is given by PV equal to nRT. P, you know, P is pressure, V is volume, N number of moles, R is gas constant, and T is temperature. Now next thing comes, that is thermal equilibrium. What does this mean? If two systems are in thermal equilibrium, it means there is no exchange of energy between them if they are put into contact. So here two systems are said to be in thermal equilibrium if they have same temperature. If there is a conducting wall between the two systems and heat does not flow, then they are in thermal equilibrium. Of course, if this is body A and this is some conducting wall. So if heat is flowing in this direction, it means temperature T1 and T2, what is the relation? So T1 will be greater than T2. That is why heat is flowing. But if T1 equal to T2, then what will happen? In that case, we can say that both are at same temperature, so there is no flow of heat. Hence, they are in thermal equilibrium. So this is basic point. Now, we are going to see sign conventions. Sign conventions make calculation easier. So, heat, work and internal energy in thermodynamics. So, heat is the transfer of thermal energy between a system and its surrounding due to temperature difference. If there will be temperature difference, then heat will flow from hotter body to colder body. It is not a property of the system, but a process of energy exchange. Then comes work. Work in thermodynamics refers to the energy transfer when a force is applied over a distance. In gases, it is often calculated as where pressure and volume is. So here, generally, work, we write F into FDS, which can be written as PdV, right? So we are talking about PdV. Then comes internal energy. Internal energy is the total energy contained within a system due to molecular motion and interactions. It depends on temperature and state variables, but not on the path taken to reach the state. Then comes sign conventions. So sign conventions are important here. So let's say heat. It is positive when heat is absorbed by the system. Means here, if this is the system and heat is entering, it means it is positive. If heat is leaving, in that case it will be negative. Then comes work. Positive work. When work is done by the system on the surrounding, means it is expanding. Suppose here this is a container that contains gas, this is piston and it is expanding. So work done by the system on the surrounding is expansion. And negative, when work is done on the system, means suppose compression is done, you are applying force and gas is being compressed, in that case work done will be negative. Then comes internal energy. So internal energy, you know that energy possessed by the particles. So here it will be positive when there is increase. It means when temperature is raised, in that case internal energy will increase, and it will be negative when the temperature drops. Correct? Then comes first law of thermodynamics. Here this is heat supplied, this is internal energy change, and here this is work done. So heat given is equal to change in internal energy plus work done. This equation expresses the conservation of energy, indicating that change in internal energy is equal to heat added to the system minus the work done. Means if you want to find out change in internal energy, then take W to that side. So here delta Q is heat supplied minus work done. So this is simple thing. Then comes isothermal process. Isothermal process means temperature is not changing. An isothermal process is a thermodynamic process in which the temperature T remains constant throughout the transformation. This means that any heat added to or removed from the system is completely used to perform work, ensuring that there is no change in the internal energy. You have understood? I can give you the example here. Suppose there is some gas in it. This is piston which is movable. Suppose you provide heat from here. So what happens? Temperature will rise. But here condition is process should be isothermal. Isothermal means delta U should be 0. So what we can do? If we pull it, then temperature will not increase, because that energy supplied from outside will be used in doing work. Same thing is given here, that this means that any heat added to or removed from the system is completely used to perform the work, that there is no change in internal energy. Suppose you compress it, in that case, here what will happen? Here temperature will rise. So in that case, energy will be transferred to surrounding. So here some examples are given. You can see a classic example of an isothermal process is the expansion or compression of an ideal gas in a perfectly conducting cylinder. Means when expansion takes place, so that is only possible when heat is applied, but temperature will remain constant, because that heat will be used up in doing the work. Similarly, if gas is compressed, in that case, if extra heat is released, so that will go, since walls are conducting, in that case it will go to the atmosphere or surrounding. Then comes isothermal expansion of gas. When the gas is slowly expanded in a container with a heat reservoir, heat flows into the system to keep the temperature constant while the gas does work on the surrounding. We have already discussed about it. Then boiling of water. During boiling, what happens? If there is state change, heat is supplied, but temperature will remain constant. So here that thing. Then equation governing isothermal process for an ideal gas is given by PV equal to constant, or PV equal to nRT. Now we are going to see work done in isothermal expansion. So here, suppose this is container, this is piston, and here there is gas, and now what happens? On giving heat, temperature rises. So here our constraint is that temperature should not rise, so that temperature will be used up in expanding the gas and temperature will remain constant. So suppose this portion is dx, right, and area of the piston is A. So volume we can easily find A into dx, which can be written as dV, but here just let's write A dx. Later on I will put it in that form. So here, suppose we want to find out work done. So work done, if initial volume is V1, final volume is V2, so we can integrate it V1 to V2, and then P A dx or P dV we can write here, P dV, right, P dV. But if you remember, PV equal to nRT, right? So from here, P is equal to nRT divided by V. So we can write this nRT divided by V in place of P. So PV equal to nRT, right? So here PdV. So P is equal to nRT divided by V and dV. Then we can integrate it, and integration dx upon x is log x. So this will become log, but log base E. Log base E is also written as, if you remember, log base E equal to ln. Log base Ex can be written as ln x. So here I have written log base Ex, and this will become V, and then nRT is there. Keep in mind, write it separately, nRT, and here limits are V1 to V2, right? And as per property of log, it will become log V2 minus log V1, which is log V2 upon V1. So nRT log V2 upon V1, right? And if you want to remove this log base E to log base 10, then you have to multiply by 2.303. So what will be your final result? So work done is equal to 2.303 nRT log, and then now it is clear log base 10, and this is V2 upon V1. So I think you have understood the work done in isothermal expansion. Now we are going to see adiabatic process. What is adiabatic process? So this is sudden process, temperature may change, etc. So let's analyze it An adiabatic process is a thermodynamic process in which no heat is exchanged between the system and its surrounding. This means that all the changes in internal energy are due to the work done on or by the system. So let's see what are the basic conditions. So perfect insulation should be there, means there should not be conducting wall which can transfer the heat, and then a rapid process. This is very important thing, that for adiabatic process to occur, the process should be rapid. If process happens quickly, there is no time for heat exchange, making it nearly adiabatic, that is rapid compression of a gas. Then comes expansion or compression should be there. The work done leads to temperature changes since there is no heat exchange. Now, equation of state for an ideal gas undergoing adiabatic process, Poisson's equation we use, and Poisson's equation says PV power gamma equal to constant. Right? Here gamma is Cp upon Cv. If you remember relation between Cp and Cv, Cp minus Cv equal to R. Right? Here value of gamma will be given when you will do some numericals, like for diatomic molecules it is 1.4. Similarly for other type of molecules it will be given, so you can easily evaluate. Now next thing is work done by an adiabatic process, means here there will be expansion but process is adiabatic. So what will happen? This is suppose initial position, this is final position, and this is piston, and this distance moved is dx, area of piston is say A. So volume will be again same thing, ADX, or you can write it as dV, ADX, so change in volume, so delta V you can write, or dV equal to ADX, or delta V equal to A times delta x. So here our concern is with the dV, so don't write delta. Now again work done can be found by same formula, integration of V1 to V2, and then here P dV, right? Because you know work done is equal to P dV, correct? Now here equation of state, PV power gamma equal to constant, right? So here we need what? We can assign the value of constant as K, and then we can proceed. So PV power gamma equal to K, or P equal to K upon V power gamma, or K into V power minus gamma, you can write. So in place of P, if we write this value, K V power minus gamma dV, then integration will give how much? It will give K V power minus gamma plus 1 divided by minus gamma plus 1, and limits are V1 to V2, right? Now what we can do, we can write it work done is equal to, here K divided by, we can write it 1 minus gamma, and then inside it will be V2 power, either you write 1 minus gamma minus V1 power 1 minus gamma. Up to here I think thing is clear. Now since PV power gamma equal to K, so you can generalize it. You can write P1 V1 power gamma equal to P2 V2 power gamma, right? So here we can take inside, and as per our need we can insert the changes. So let's take it here. So W is equal to 1 upon 1 minus gamma times, in place of K, here we can write P2 V2 power gamma, P2 V2 power gamma into V2 power 1 minus gamma, correct? And then minus for second one, it will be P1 V1 power gamma into V1 power, it is 1 minus gamma, correct? So W equal to how much? This gives W equal to 1 upon 1 minus gamma times inside what we are getting. Here gamma will cancel out, P2 V2 minus P1 V1, or write it like this, 1 upon gamma minus 1, then it will become P1 V1 minus P2 V2. Up to here, no problem. Now we can apply PV equal to nRT. So we can generalize it, P1 V1 nRT1. So this will become 1 upon gamma minus 1 nRT1 minus nRT2, right? Or we can take out nR divided by gamma minus 1 times T1 minus T2. So this is expression for work done by an adiabatic process. So this is all for this lecture. Thank you for watching. Team Educate.